We've been talking about the difference between data type-oriented programming and object-oriented programming. With data type-oriented programming, you can add new operations without changing your existing code. And with object-oriented programming, you can add new variants without changing your existing code. But if you add new operations, you need to change the existing variants, or in data type-oriented programming, to add new variants, you have to change the existing operations, the existing functions. Sometimes people, including me, will say functional programming versus object-oriented programming when we really mean data type-oriented versus object-oriented. But there's another sense in which we might say functional versus object-oriented programming, and that's in the set of primitives that we have, where functional is again this notion that you have functions that you can nest and create arbitrarily, versus object-oriented programming where objects are the key thing instead of being just implemented with functions. That is, when we implemented a rectangle object like this, we were relying very much on the functions in Plait to be able to form a closure and capture the W and H in that area method, for example. And so we need all of the machinery to do that. But there's a different alternative, which is to have objects that have fields and methods and no closures. The object takes over that role. So here I've got not a function, but a macro rectangle, where this is rectangle init w init h is really going to be shorthand for writing this pile of code. And in this pile of code, even though we're using a lambda, there are no free variables in this lambda. Instead, we could have written this as r area and r bigger than as top-level functions, which are not nested or in anything. And then all we have to do is create a tuple that contains a couple of lists. The first list maps field names to field values, and the second list maps method names to methods implemented as first-order functions. Where we used to just refer to W, we have to use this get operation to get the W field out of an object. And correspondingly, our area method has to take this explicitly as an argument. Using this strategy, we could redefine shapes as having this kind of structure. It'll be a tuple to have a list of fields and then a list of methods, where each method is a tuple with a name and a function, but now the function has to take the object itself as a first argument so that it can access these fields. We'll have a helper macro get, which makes it easier to get the value of a field. So if you've got an object, the way you get the value of the field is you take the first part of the tuple here, and then you find the field name in that list, and then the value you get out is the field value. So we can have a rectangle constructor that when it's using get this W is taking the shape this and looking for the W field in its list of fields, so it'll get whatever we initialize the rectangle with here. And then we'll also have a helper method send, which makes it easier to call methods. When you have an object expression, we'll give it a name O, and then we take the second part of the O to get to this list of methods, like this list of methods here with area and bigger than. We'll use find to find the method that we want, maybe area, maybe bigger than. That will give us an object, give us a procedure, and then we call that with our object, right, that goes in for the this argument, and then any other arguments that the method is expecting. So, for example, if we construct a rectangle R, then we can send R the bigger than message, passing it the argument 200, and it'll check whether the area is bigger than 200. Here, instead of repeating the area calculation, we can now call the area method on this.